In this module, we shall look at techniques for randomized allocation of treatments in a clinical trial. As you know, the clinical trial is considered the gold standard of study design and at its simplest is a double-blinded, placebo-controlled clinical trial. The assumption of randomization is extremely important for clinical trials, and it is what guarantees that the results can be considered to be scientific. It is a guard against the typical kind of biases such as selection bias which creep up in many epidemiologic studies. So here we shall look at the actual methods for randomization. At its simplest, we shall have two treatments and we can consider repeatedly tossing a fair coin so as to get allocation to two treatments, A and B say. However, we often opt for more complicated designs, and one reason for this is to guard against any accidental bias. So we shall also look at block allocation for the case where the patients arrive sequentially. We shall look at a technique called minimization, Efron's biased coin design, and finally we shall look at the SRS package in R to see how minimization could be implemented. Learning objectives for this module. We shall look at first the justification for randomized allocation. So why randomize? Next, we shall look at the simplest case where it is necessary to randomize patients to two arms of a clinical trial. We shall look at some variants considering the cases where patients arrive in a sequential manner and also methods which guard better against accidental bias. Finally, we shall look at the SRS package in R which provides a means for minimization based randomized allocation. We assume that we have two independent groups, though of course it is easy to generalize the methods to the case where we may have more than two. The two independent groups are accomplished via randomization. Two group problems can arise in different situations. So we have the two group problem for superiority, where we wish to explore whether one treatment is superior to another on some relevant primary outcome. We can have the two group problem for non-inferiority, that is, we wish to test whether a new treatment is no worse than an existing treatment with respect to this outcome. We also have the two group problem for equivalence. So here we wish to test whether two interventions are essentially identical to one another with respect to some pre-specified outcome. The use of randomization is essential, and this is for the generalizability of the results as well as for the validity of the inference. Distinction between simple random samples and random allocation. Simple random selection and random allocation are not the same thing. By random selection, we mean a simple random sample of size k, for example, means that each individual in the population has the same equal probability of being selected, and as a result, each possible subset of size k in the population also has the same chance of being selected. The reason why simple random sampling is used is the hope that it will help with the external validity of the results as well as allow them to be generalized to a larger target population. Random allocation, on the other hand, is a procedure in which sample participants are randomly assigned to treatments, and each participant must have the same probability of being assigned to any particular treatment. If the design is based on capital N participants and small ni are to be assigned to treatment 1, then all possible samples of size ni have the same probability of being assigned to treatment 1. We next come to the important case of why we should randomly allocate. So say we have a situation where treatments have not been randomly allocated, and there are two treatments A and B which we wish to compare to look at their efficacy. Suppose either by accident or by purpose, treatment A is allocated only to men and treatment B only to the women. If we look at the estimated treatment difference, which is the difference in the mean outcome between the two groups on A and on B, this treatment difference could arguably be either the effect of treatment or the effect of gender or some combination of the effect of both. It is not possible to make any statement about these treatment effects because it is completely confounded in this case with differences in the effect of gender. So in statistical terms, we have confounding and also unidentifiability of the underlying parameters. From an epidemiologic perspective, we have introduced systematic bias by allocating treatments of one type to one specific gender only, and thus being unable to ensure that the results from the treatment differences are free from scientific bias. Let us first then look at the simplest case of randomization. So we are assuming that we have two treatment comparisons. We also have a predetermined overall sample size capital N and a predetermined sample size of small n for treatment 1 and small m for treatment 2. Of course, m plus n is equal to capital N. In many situations, small n and small m will be equal. So there are various ways of making treatment allocation. We could toss coin, we could roll dice. We could, for example, have a total of capital N envelopes, of which n contains some identifier for treatment 1 and m contains some identifier for treatment 2. We can shuffle the envelopes, and the order of the shuffled envelopes will determine the allocation of subjects to treatments. We can implement the same kind of an idea by drawing balls from an urn. We often have cases where it is necessary to use simple sequential randomization. A commonly encountered situation is a two-group comparison where the sample sizes are required to be approximately equal for a two-group trial. So in this case, we have a situation where we are tossing a coin such that each participant has an equal probability to be allocated to either of the treatments. If the sample size is relatively large, we will expect to see approximately equal sized treatment groups. However, if the sample size is small, then this is not always guaranteed, and general recommendation is to use such simple random sampling only if the overall sample size is large, such as above 200. So, a possible problem with simple randomization is that simple randomization in principle will reduce bias by equalizing on factors that have been not accounted for in the treatment design. So, say for example, if gender is an important factor, in the long run we would expect that on average the gender distribution is similar in both groups. However, there is always a chance of imbalance, which is called accidental bias, which can occur if the gender of the person is not taken into account itself into the treatment allocation procedure. When we perform sequential randomization, a common popular technique is block randomization. So, block randomization is used in a two treatment situation, for example, when the sample sizes for the two treatments are to be equal or approximately equal. So, here we recruit participants in small blocks and in such a manner that we ensure that half of the participants within each block are allocated to treatment A and the other half to treatment B. Within each block, however, the order of the patients is random. So, suppose we are considering blocks of size 4, then there are 6 different possibilities, that is AABB, ABAB, ABBA, BAAB, BABA and BBAA. To implement this procedure, we select randomly among these 6 different blocks for each group of 4 participants that are recruited. This can be done automatically within many software packages, including SPSS, Excel, and of course SAS and R. Another alternative means of random allocation is the case where we have stratification. So, a stratification factor is a categorical covariate which divides the patient population according to its levels. So, say we have measured in addition to treatment several covariates including gender, which has 2 levels, male and female, age, which we can choose to categorize in terms of 3 levels, say less than 40, 40 to 59 and greater than equal to 60. Recruitment centers, any other prognostic factor and so on. In this case, we do not perform the allocation overall, but treatments are allocated within each stratum. Another common technique is minimization. This is a means of guarding against accidental bias. So, here the first patient is randomly allocated, and for each subsequent patient the treatment allocation is identified, which minimizes the imbalance between groups at that time. So, to use an example, let us suppose that we have 3 stratification factors, gender with 2 levels, age with 3 levels, and say disease stage, which also has 3 levels. Suppose we have a situation where 50 patients have been enrolled and the 51st patient is male of age 63 and stage 3 disease. Then We can either count only the sign of the difference in each category. So we look at all the males and see whether there are more on treatment A than on treatment B. We can look at everyone age 63 and do the same, and similarly for the stage 3 disease. Or we can add the total overall categories. So say there are 26 A's versus 24 B's, and then since treatment A is ahead, we will assign this patient to treatment B. So usually these criterion will agree, but not necessarily so. Both criterion, however, will lead to a reasonable balance. An interesting design is based on Ephron's biased coin design, which appeared in Biomedica in 1971. So assume we have two arms in a clinical trial. The idea here is to keep changing the allocation probability to treatment A as the trial progresses, so as to keep the balance in each group nearly equal. So let us assume that so far small n equal to capital NA plus capital NB patients have been allocated, where NA is the number assigned to A and NB is the number assigned to B. Let P equal to the probability that a subject gets treatment A, and let us also define the running difference D equal to NA minus NB. The probability of allocation is then defined as P equal to half if D is equal to 0. So if at some stage we have NA equal to NB, subjects are allocated to either treatment with probability half. However, given that D is non-zero, we shall allocate subjects to treatment A with probability 2/3 if D is negative and 1/3 if D is positive. So this is analogous to tossing a biased coin. So note that NA, NB, D continuously change with each new subject, and so does P. Variants of this design have been proposed. For example, the EARN designs of Way and Lachlan, which can be found in Controlled Clinical Trials 1988. Finally, let us look at the R package SRS, which implements the procedure of minimization. So it provides two S4 classes called Clinical Experiment and Pocock-Simon Randomizer. The typical usage is that we first construct the clinical experiment, we construct the Pocock-Simon Randomizer class using the clinical experiment as an outcome, and then we call the randomization method with certain subject-specific inputs. So here we are calling library SRS. We are constructing the clinical experiment as experiment is clinical experiment. The number of factors is 3. The factor names is C, sex, age, and stage. The number of factor levels is C, 2, 3, 3. Factor level names is a list containing C, female, male, C less than 41, 41 to 60, greater than equal to 60, C 1, 2, and 3. The number of treatments is 2, and the treatment names are A and B. We construct the randomizer class as randomizer is new Pocock-Simon randomizer. experiment equal to experiment with a random seed. To implement this, we would use randomizer is randomize subject ID equal to something and factor values say male greater than equal to 60 and 3. Then using the function last randomization randomizer, we can get the treatment allocation for this subject. In this module, we have looked at alternative techniques for randomization. As you know, randomized allocation of treatments is extremely important in clinical trials for the validity and the generalizability of the results. We often use randomization and its variants to guard against accidental bias introduced into the study design. At its simplest, we can consider tossing a fair coin or a die to allocate patients to the different treatment arms, but often we are required to consider more complicated situations. Thus, we have also looked at sequential trials where we can consider block allocation. We have looked at minimization methods. We have looked at a design which is due to Efron and is called the biased coin design. We have also looked at the SRS package in R and seen how we can implement minimization in a practical situation.